Today, we want to continue in looking at integration by substitution, the anti-chain rule. The parts that we're trying to identify are an inside function. Once we do that, we can identify an outside function. Then we look for the most important part. What is going to be the derivative of the inside? What's our dw? Once we decide on the inside, we have to make sure that we have a constant multiple of the derivative of the inside. That's what makes the substitution work. So let's take a look at this example. We've got a 2x times cosine of x squared plus 1. And it really only looks like we have one candidate for an inside function. Inside is the first part of a composition of functions. 2x is being multiplied by the cosine, but we have the cosine of x squared plus 1. Looking at this quickly, we see the x squared on an inside some other function, and we see the 2x. That's going to be the derivative of the inside. Our outside function will be cosine. That's what we're going to be integrating. So our setup, we'll say w is x squared plus 1. We'll take the derivative of this to make sure our substitution will work. So we've got exactly what we need to make substitution work in this case. If w is to be x squared plus 1, then the dw will need to look like 2x dx, and that's exactly what we have. Our outside function is cosine, so f prime is cosine. So we'll be integrating the cosine of w, because the x squared plus 1 gets replaced with w. And this substitution will work because I've got this 2x dx as a factor. That 2x dx, all of that is our dw. Now we have the integral of an integral dw, which is easier to integrate. The whole point of this is that we will recognize the resultant integral. The integral of cosine is negative sine because the derivative of, the integral of cosine is sine because the derivative of sine is cosine. Then the last thing we have to do is replace the w with our expression in x. Last time we focused on a lot of substitutions that weren't going to work. We were looking at the function, we're looking at this x squared plus 1. That's still in use this week. The important thing to recognize here is that we need, if we want to make the substitution w equals x squared plus 1, we need a factor of x to be the dw. That's what we need to make this go. We need a factor of x to make dw. To make this substitution, if we want to make this substitution, then we need a factor of x to be the dw. The big question when you're doing integration by substitution is what's going to be my dw? That's what makes the substitution work. It doesn't need to be exact. It can be off by a constant multiple, but that's the biggest difference that we can have. Our DW can be off by a constant multiple. So the only difference we can have, this can be off by a constant multiple. This can only be off by a constant factor. I don't need 2x. The important part is the x. The 2 is just, it happens to match perfectly. So if I just have an x, cosine of x squared plus 1 to x, the substitution will still work. If I want w to be x squared plus 1, to make this work, I need a dw that's a constant multiple of 2x dx. The important part of this dw is the x dx, not the 2. The 2 is just a constant factor, and I can divide both sides and still make it work. I'll just say 1/2 dw is equal to x dx. We're still identifying our outside function as cosine. So our cosine of x squared plus 1 is going to be a cosine of w. And in this case, the x dx becomes 1/2 of dw. I usually write the constant out in front because it's just a constant factor. These two parts go together, in case you're not taking your notes in glorious Technicolor. It just pulls out this constant factor of 1/2. So when we integrate, we end up with not just sine of w plus c, but a 1/2 sine of w plus c. So our answer is a 1/2 sine of x squared plus 1 plus c. The important part is the x, not the 2. The idea of looking for this stuff is that we want to be proficient enough to look for this stuff that we don't have to run through the process. We want to look at this integral, recognize that the 10 doesn't matter, that this is going to be a substitution, and this is going to be a 1/2 sine of x squared plus 1. Then we'll just multiply by 10. So 5 sine of x squared plus 1. The goal is to write down 5 sine of x squared plus 1 plus c and nothing else. Even if I say, show your calculations happened in your mind. And you look at this and say, well, this is just going to be 5 sine of x squared plus 1 plus c. That is the goal. The goal is to be able to just write down the answer and not have to go through all the details. The goal of every math class is to stop writing all the details. Understand the details well enough that you don't have to write them down. Everything works out the same if W is, or we still want to make W an x squared plus 1. To make that substitution work, I need some multiple of 2x to x. Back when I learned integration by substitution, I was programmed with this style of work. To recognize that the x dx was the important part, is get rid of the 2, and then put that back when I replace the x dx. The goal of writing this down is to recognize that x dx is the important part, not the 2. So that's the reason for writing things in this particular style. The 10, I always pull out of my integral, and then it gets multiplied by the 1/2 from the dw. So that's where the 5 comes from. We want to be able to see that without having to go through the details. If you were going to write the details, my recommendation is you take once you write down the dw just by taking the derivative, you recognize what the important part of your dw is. How's everybody okay? It's too much for a Monday. It only seems like a lot to remember because it's a lot to remember. You have to remember all of it all the time in perfect detail. No problem. After 3 integrals where substitution worked just fine, we have to have an integration where substitution isn't going to work. Take a look at this integral. I have just stated that this integral is not going to have, we can't do this integral with substitution. This is not entirely true. We can do half this integral with substitution. What part of this integral can we not do with substitution? So if we look at this, we want to make our substitution. The only candidate we have for an inside function is x squared plus 1. The derivative of x squared plus 1 is 2x. And it looks like I have that, but I don't exactly have 2x. I've got 2x plus 3. And that plus 3 messes everything up. That plus 3 changes what we need for a dw. So when we say w is equal to x squared plus 1, then what we need for our dw is a 2x dx. We can only be off from the 2x by a constant factor. In this case, 2x plus 3 differs from what we want for dw by a constant term. So that 2x plus 3 is not helping because of the plus 3. This is only half a substitution problem, and we'll have to split the terms to do it. One term will be integration by substitution, the other term will not, and we don't know it yet. So I could split this into two integrals just with the distributive property. This could be a 2x times a cosine of x squared plus 1 dx plus 3 times the integral of cosine of x squared plus 1 dx. So here, this first one is substitution. So this first one we can integrate and write a sine of x squared plus 1. But this second one, we don't have anything. Actually, we would have plenty because we have access to Wolfram Alpha. We just look it up. For substitution, our technique that we're studying right now is not going to work because if I want w to be to x squared plus 1, then dw is a 2x dx. The important part being the x dx, and we haven't got that. I would need another factor of x to make that substitution work, so that substitution will not work. Is everybody okay? It's hard to read if everybody's okay and everything, and these problems are just too easy. You're like, oh, these problems are below us. We're going to look forward, and it looks like this. Or these problems are super confusing. I will just act tough, like I understand, and then worry about it later. Like no one wants to ask questions in class. I get it. The teacher is always cast as the enemy, and you don't want to show any weakness in front of your enemy, even though my literal job is to answer your fucking questions. But that's all right. When you don't ask questions, my assumption is you get what I'm talking about, even though I know at some point that is not going to be. But I just like, all right, we'll play our little student teacher game. You'll go try to learn it on your own. Then you'll feel like, depending on what your view of yourself is, you'll feel like I must be the only student that doesn't know what's going on. Meanwhile, it's only you and 39 other people that don't know what's going on. And instead of like going to a room and like comparing notes, like, oh, did you know what he's talking about? I have no idea what he's talking about. He's being completely obscure. And then realizing that I'm the problem. Hi, it's me. I'm the problem. You all think y'all are the problem. You know what I mean? Does this sound familiar? Some of you, it doesn't sound familiar because like, oh, I have never had a question ever in math class, which is good. You just have to go through the math classes, do the stuff. I say integration by substitution is the anti-chain rule, and instantly your homework is all complete. Everything is fine. I don't know, some students are like that. They haven't hit a wall yet. And other students are like, oh, this shit has been hard ever since like arithmetic. And it's just nothing but a struggle. Let's look at a variation of this problem. Let's move some stuff around. Right now, our first problem had a cosine of x squared. X squared was plugged into a cosine. Let's just switch that around. Let's take the cosine and plug it into a square. Now, this on its own is not a substitution, but remember when we see cosine squared x, this means the square of the cosine of x. First, x gets cosigned, then we square the result. So make sure that we can read this right. I want to make this a substitution problem, and I want cosine to be the inside function. That means I'll need a sine to be the dw. Derivative of cosine is negative sine. I would need a constant multiple of sine of x to be the dw. So let's just start off with our nice basic substitution problem. So the important thing here is how we read cosine squared. Cosine squared is our shorthand for writing the square of the cosine of x. I wrote dw, I should be writing dx. So make sure that when you see cosine squared, you think the square of the cosine of x, so that the cosine is your inside function. If w is to be cosine x, then the dw needs to be a multiple of negative sine x dx. Because derivative of cosine is negative sine. I don't exactly have sine x. The important part is not the negative. The important part is the sine x to x. Oh, and our outside function, the thing that we're actually integrating is something squared. So we're integrating w squared. There's our inside. Here's what's happening to it. And then sine x dx is going to be replaced with a minus and the dw. Now I've got our integral in w. So we've gone from our integral in x to an integral in w. Now we integrate. So minus 1/3 w cubed plus c. And then we go back to our original x. It's functions like this. As a side note, it's functions like this where I really care about getting practice using the equation editor to type this stuff out. Because when we write this with the vertical fraction out in front and the cosine cubed of x in our weird powers of trig functions notation, it's easier if we can write this as a picture. If we can use the equation editor to display a picture. Writing this in single line syntax becomes very difficult to read, partially because of the number of parentheses that we need, and partially because of the huge variety we have in how we can write this. So just as a side note, so we have the cube of cosine of x. We know we can type that as cosine of x close to the third power. Because this clearly demonstrates that x gets the cosine, then we raise the result to the third power. To get the minus 1/3, it's best practice to put your coefficients in parentheses when they're fractions. Question? Can you do what? No, we need no, we need W to be the sign. If we make W, sorry, if we make W equal to sign, then the derivative is cosine, or W, dW is being squared. Right, we would have, there would be too much there. So we wouldn't have a W, we would have one factor of cosine to be the dW, but we wouldn't have an answer for the other factor of cosine. We wouldn't be able to write the cosine as a W. So if I had to write this in single line syntax, this is probably what I would do. It would be technically okay to write this as, let's say, -1/3 cosine cubed x. I don't know why writing cosine cubed x like this in single line syntax is so offensive to me. There's something wrong with it. I don't know if there's anything technically wrong with it, but it pisses me off no end. I don't know why. If you've done this already, it would have been the first time you're attempting to type this. So I wouldn't be mad. But if it keeps up, I don't know. It's irrational. I know, because it says what we need to say. Also, if the internet has taught us anything, most people will read this 1/3 cosine cubed x as 1/3 cosine cubed x. But some people will definitely read this as PEMDAS, which is just not correct at all. What that means is putting a division and a multiplication lined up like this reduces clarity. You're expecting people to read this exactly like you would read this. Say, well, divide by the 3 and then multiply by the rest. Obviously, this 1/3 is supposed to be the coefficient. When you start making assumptions like that are not standard and just when you start assuming that people view the world that you do, you're communicating very poorly. It doesn't matter if you're technically correct if your message is not going to be received. Does that make sense? This is important in all categories. It does not matter if you are technically correct if your message is not going to be received correctly. And the failure in that is not the receiver. The failure in that is the communicator. You try to communicate something, the person to whom you're communicating misunderstood. That means you need to clarify. That make sense? Now, if the person receiving your message is deliberately misconstruing what you said, it's still your fault. You need to say stuff where it can't be misunderstood, deliberately or otherwise. If you could have improved your message, then you should have improved your message. Does that make sense? That's why I don't like this single line syntax. That's why I'm requesting things come out in equation editor. Partially because I gotta be the bad guy. If you write something that could be misconstrued, I get to misconstrue it and say, oh, that's not what the right answer is. I don't want to divide by these cosine. And you're like, well, I didn't mean to divide by the cosine. At which point, it doesn't matter what you meant to do. You failed to communicate your message. Does that make sense? Clear communication is the key to success. As a demonstration, some of you have been in my class before, and so you've seen this demonstration. I'm going to write an expression down. I want you to speak this expression to me and make me write it down. in such a way that you're not just spelling it. That's not how we communicate. We don't just spell things at each other. It's efficient. As a person who shares, whose last name is a homonym with a black blood-sucking worm, I usually just spell my last name for brevity. It's the L-E-A-C-H, not an L-E-E-C-H, even though not only are those words homonyms, historically, they are synonyms as well. My last name is Leach because some member of my family in my ancestry probably made their living by attaching leeches to people to pull out the bad humors. But if we write down an expression, it's hard. The reason that we have this is because it's very clear what operations I want to perform and the order that I want to perform them. But when we write a sentence to describe what's going on here, it doesn't come out very well. Think about how you would say this: 2 times x minus 5 cubed. But if you just said 2 times x minus 5 cubed, I wouldn't necessarily write this down. If you said, for example, 2 times x minus 5 cubed, no, that's not what I wrote. Now, you might think, I'll be fancy and I'll use the word quantity. The problem with using the word quantity is that, first of all, you say quantity to open up the parentheses, but then you never close the parentheses. So it's never clear what you're talking about being cubed. And furthermore, when you say the quantity, you're just spelling it. You might as well just say 2 open parentheses, x minus 5 close parentheses cubed. But even if you're like, 2 times the quantity, there's nothing in this expression that says anything different from the previous one, only you just think you sound fancy because you're like, the quantity, but you don't. You're still miscommunicating. This still can easily be read 2 times the quantity x minus 5 cubed. Still a miss. And if you turn back and rely on the fact that, well, the quantity means, like the next operation. Now you're making assumptions that the person to which you're trying to communicate will definitely interpret things the same way you do. The quantity is not enough. X is a quantity, and x minus 5 is also a quantity. Also, if you're like, the quantity applies to the next operation, someone tried that one on me. The quantity applies to the next operation. I say, I see. So if the quantity applies to the next operation, 2 times the quantity of x minus 5 cubed. Got it. Well, shoot, that's just 2x minus 250. That's still not what I wrote. That make sense? This is why I want with the equation editor, because in the equation editor, you can make it look like we write it on paper and not have to worry about getting your parentheses right in single line syntax. Especially because after I point this out, some of y'all go crazy with the parentheses. It's just like parentheses everywhere, which is also kind of funny. Any questions? Yes. So this would be 2 times the cube of the difference between x and 5. Two times the cube, so it's 2 times the cube of something. The cube of what? The difference between x and 5. The difference specifies that we're subtracting, and it's an improvement on the expression, the quantity. And the order that I said those things is important, because this first one says 2 times the quantity x minus 5 cubed. So if we use the rule, if the quantity applies to the next operation, it's not 2 times the difference, it's 2 times the cube. We got to make sure that we get that in the order. Here's how to speak things that you speak expressions without spelling them. What's the order of operations? First thing that happens to x is we're subtracting 5. Second thing that happens to x is it gets cubed because the order of operations. And then the last thing that happens to x is we multiply by 2. Agreed? Order of operations says this is what you would do. If x is equal to 10, 10 minus 5 is 5, 5 cubed is 1.5 times 2 is 250. That's the order of operations, how we would evaluate. If you want to read the expression, read it in the reverse order. Read it this way. Two times the cube of the difference between a number and 5. No one can write down anything but this expression if you speak it that way. This would commonly be read as 2x minus 5 cubed, but 2 times x minus 5 cubed, that's this down here. But if we write down things in the order of operations, first we multiply by 2. Second, we subtract 5, and third, we raise to the third power. That's the order of operations that we would perform. If x is equal to 10, 10 times 2 is 20, 20 minus 5 is 15, 15 cubed is 15 cubed. 3 5s and 3 3s. But if we want to read this expression so that this is the only expression that can be written based on the description, you read it this way. The cube of the difference between 2 times a number and 5. The cube of what? This difference. The difference between what? 2 times this number and 5. Any questions? This strategy is also how we solve the equation. If we want to write the inverse function would be first do the 1/3 power, then add 5, then divide by 2. That's the steps that we would take in solving an equation. If the cube of the difference between 2x twice the number and 5 is equal to 13, then the first thing we do is cube root. The second thing we do is add 5. The third thing we do is divide by 2. How to read it is how we solve the equation. This particular strategy only works when the variable appears only once. So if we have a quadratic equation and the variable appears twice, then we can't read it in this simple fashion because there's not just one x where everything is happening. Except for the fact that I said it's quadratic. So instead of writing ax squared plus bx plus c and using the stupid ass quadratic formula, which is trash, we would just complete the square and rewrite it in its vertex form, emphasize that the graph of a quadratic is a parabola, and utilize the symmetry of the parabola to solve our problem. Rewrite that as a times the square of the difference between x and h. Let's see, the sum of a times the square of the difference between x and h and k. Get a parentheses x minus h closed parentheses squared plus k. Then the x appears only once, and we can perform inverse operations in reverse order. We can emphasize the fact that the middle of this, where the vertex is negative b over 2a. And then we're going to have the same amount above and the same amount below. Utilize the symmetry. But that's all beside the point. Really what we care about is what's our DW? That's what makes the substitution work. We can be off by a constant factor. We cannot be off by a constant term. And we cannot be off by an x. Your goal is to identify the important part of the DW. For x squared, I need an x. Any questions? All right, it's just going to be more integration by substitution tomorrow, so more training. What's my DW? That's what we need to think about. That's it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.